Well, there's this idea that floats around, this sense that space exploration is a kind of grand strategic choice, a move on a cosmic chessboard to save humanity. And there's a truth to that, of course, but I think it runs deeper. It's not just a strategy, it's a form of care, a profound, almost parental care for the future, for the continuation of this strange, wonderful and fleeting thing we call life. Our planet, this beautiful blue marble, is our ultimate home, there's no question. But you can't help but get the feeling that it's becoming a bit crowded, not just with people, but with problems. Problems on a scale that can't be solved locally anymore. We found ourselves in a precarious moment, haven't we? We've navigated decades filled with pandemics, with climate extremes that feel less like anomalies and more like the new normal, with conflicts that ripple across the globe. We experience migrations driven by droughts, by wars, by the simple, desperate search for stability. Water, food. These fundamentals are becoming points of contention for so many. The delicate tapestry of our ecosystems is fraying at the edges. We've reached a point where there's nowhere to hide, really. There are no safe corners left where everything is stable and predictable. The world has become one interconnected system, for better and for worse. And so, we cast our gaze outwards, and our gaze, for a very long time now, has settled on Mars. We perceive that distant world with a complex cocktail of emotions, a bit of fear, a great deal of excitement, and an enormous amount of hope. The red planet isn't just an object of scientific curiosity anymore, it's become a mirror, a challenge to each of us. It forces us to ask whether we're ready to step beyond our cradle, not just to seek new horizons, but to build a future far from the only home we've ever known. And this isn't a new question, not really, it's the oldest question. Humanity has always peered into the darkness, trying to understand what meaning lies just beyond the edges of what we can perceive. It all began with a simple act of observation. Ancient astronomers, lying on their backs on a clear, dark night, began to notice something peculiar about one particular point of fiery red light. At first, they thought it was a star, just another fixed jewel in the celestial sphere. But as they charted the heavens, night after night, generation after generation, they discovered a profound truth. The stars, the asteres, they move with a predictable, almost stately regularity. They appear in fixed patterns, what we now call constellations, wheeling across the sky in a grand, dependable cosmic dance. But Mars and a few other wandering stars behaved differently. They moved. They drifted across the backdrop of the constellations, as if following some invisible, intricate path of their own, as if they were lost, or perhaps as if they were searching for something. Just a few of them, tracing these slow, deliberate arcs among the fixed points of light, their positions subtly shifting from one night to the next. What were they? What was this deviation from the cosmic order? The Greeks, with their gift for elegant description, called them planetae asteres, wandering stars. Over time, the name was shortened, leaving us with just one word, planetae, our planets. The word planets literally means wanderer, or one who goes differently from the others. Isn't that beautiful? It's more than beautiful, because it's so deeply true. Planets don't shine with their own light, as stars do. They are wanderers in the dark, catching and reflecting the light of our sun. And they move in these wonderfully complex trajectories, arcs and loops across our sky, almost as if they possess a will of their own. And Mars was the strangest wanderer of them all. After travelling in one direction for many months, it would seem to pause, brighten in the sky, and then reverse its course, travelling in the opposite direction for a time before resuming its forward journey. This bizarre behaviour, combined with its blood-red colour, led our ancestors to associate it with war, with violence, danger, and death. It's no surprise that ancient cultures named the planet after their gods of war. For the Greeks, it was Ares. For the Romans, Mars. Thousands of years have passed since Mars was just a mysterious red wanderer in the night sky, but our fascination with it hasn't diminished in the slightest. If anything, it's grown more intense. Since the 1960s, our sophisticated technology, our robotic emissaries, have given us a wealth of knowledge. Yet for every answer we find, a dozen new questions seem to spring up. For example, while it seems incredibly doubtful that life as we know it exists on Mars today, was there a time when it did? And if so, what happened to it? The apparent absence of life is likely tied to the planet's lack of liquid water, which is another profound mystery. We have such strong evidence that water once flowed freely across its surface, forming rivers and lakes, perhaps even oceans. But now there appears to be no trace of it on the surface. What made it vanish? And why should we even bother exploring Mars? Well, as our exploration continues, more pieces of this grand Martian puzzle will surely fall into place. But some people do question whether it's worth the effort at all. Space missions are staggeringly expensive, costing billions of pounds each year. Yet scientists are convinced that the exploration of Mars is crucial and must continue. And the reason for that conviction is simple and profound. Mars is so very similar to Earth. About 4 billion years ago, when the two planets were young, they could have been nearly identical, a pair of planetary twins. Geologists believe there was a time when Mars had a warmer, wetter climate, vast oceans of surface water, and an atmosphere very similar to our own. But somewhere along its 4.5 billion year journey, Mars underwent a catastrophic transformation. It's as if the entire planet was gripped by a global, irreversible ice age. Today, its surface is a dry, sterile desert. Its atmosphere is a ghost, too thin to support life as we know it. And its average daily temperature is more bone-chilling than the coldest place on Earth. What could have caused such a radical, world-altering change? And here is the question that sends a shiver down the spine. Is Earth destined to suffer the same fate? But long before we could even formulate such questions, Mars had already captured the human imagination. Those who first tilted their heads to the heavens and studied that red dot weren't just astronomers. They were people possessed by a fundamental need to understand what was out there, beyond the familiar. And the next great leap in that understanding began in the early 1600s, in the Netherlands. A strange new device appeared in a workshop, a simple tube with glass lenses at each end. It didn't look like much, but it did the impossible. It brought distant objects closer. It was the dawn of a new era. Word of this invention, which would come to be called a telescope, spread like wildfire across Europe, and it caught the attention of an Italian scientist named Galileo Galilei. Although Galileo had never experienced the device himself, he was so intrigued by its potential that he set about designing and building one of his own. A devoted observer of the sky, Galileo intended to use his new instrument to study the stars and planets in a way no one ever had before. His model, which resembled a small pair of binoculars, used a set of glass lenses to achieve magnification. When he peered through it, objects appeared about 30 times their normal size. Now, he probably wasn't the very first person to point this new invention at the night sky, but his was the first systematic and, crucially, published study of celestial bodies using it. And what he perceived was revolutionary. He discovered that the great planet Jupiter had its own retinue of moons, tiny points of light dancing around the gas giant. He marvelled at the moon's uneven surface, scarred with craters and etched with valleys, revealing a world far more complex and Earth-like than anyone had imagined. And then there was Venus, shining brilliantly, displaying phases just like our own moon, a key piece of evidence that would shatter the old worldview. In the year 1610, Galileo published Sidereus Nuncius, or The Starry Messenger, a book that was slim in size but monumental in its content. In it, he described his observations, the mountains and craters of the moon, the thousands of previously invisible stars that made up the Milky Way, the phases of Venus, and most importantly, the 4 largest moons of Jupiter. He named them the Medicean stars, a clever nod to his patrons, the Medici family. Galileo's telescope was a gateway to a new universe. His discoveries ignited fierce debates among scientists and philosophers, forcing many to question humanity's place in the cosmos. Was the Earth really the centre of everything? Or was it just one of many worlds, a wanderer among wanderers? However, Galileo's work was met with fierce opposition from the Church. His conclusions directly contradicted the accepted doctrine, which was built upon the geocentric model of the universe, with a fixed, unmoving Earth at its heart. The opposition from the authorities was immense, but it didn't break Galileo. His passion for discovery drove him to continue observing, documenting, and sharing his findings with the world, paving the way for generations of astronomers to come. Thanks to Galileo, the night sky was no longer just a beautiful backdrop to human life. It became a vast, deep expanse of wonders waiting to be explored. Each new observation didn't just push the boundaries of human knowledge, it inspired all those who dared to lift their heads and try to comprehend what lay beyond the visible. Before Galileo's time, our understanding of the universe was shaped by ancient thinkers like Claudius Ptolemy, a Greek astronomer and mathematician who lived in Egypt in the 2nd century AD. Ptolemy championed the geocentric system, the idea that the Earth was the stationary centre of the universe, and that the Sun, the Moon, the planets, and the stars all revolved around it. Carl Sagan, in his wonderful book Cosmos, called this the most natural thought in the world. I mean, you can feel it, can't you? The Earth feels solid, stable, and unmoving beneath our feet, while the heavenly bodies glide serenely above us. Throughout the Middle Ages, Ptolemy's theory was widely accepted, particularly by the Roman Catholic Church, which saw it as a perfect reflection of biblical teachings. To question this system was to risk accusations of heresy, with the most severe consequences. So, many scholars simply remained silent, but the Renaissance ushered in a new era of fresh ideas and bold thinkers who were willing to challenge the established order. One of them was Nicholas Copernicus. After 30 years of painstaking observation, he published De Revolutionibus Orbium Coelestium, or On the Revolutions of the Heavenly Spheres. In this seminal work, he presented a revolutionary idea. The Sun was the centre of the universe, and the planets, including our Earth, revolved around it. Copernicus argued that the Moon was the only celestial body that orbited the Earth, while the other planets followed their own paths around the Sun. This concept became known as the heliocentric system, from the Greek word helios, meaning sun. Copernicus was acutely aware of the controversy his ideas would cause, so he chose to publish his work shortly before his death in 1543. His book marked the beginning of a new scientific age, but his model, though revolutionary, was incomplete. For instance, Copernicus still believed that the planets moved in perfect circles, an assumption that would later be proven wrong. Nor could his theory fully explain the perplexing retrograde motion of Mars, which continued to puzzle scientists. It's a classic example of how science works, isn't it? A brilliant leap forward, but still constrained by the assumptions of the time. The idea of the perfect circle was an aesthetic, almost philosophical inheritance from the ancient Greeks that was hard to shake. It was only several decades later that Copernicus's work captured the attention of scholars like Tycho Brahe. This Danish astronomer was a fascinating figure. He didn't fully accept either the geocentric or the heliocentric theory, trying instead to find a compromise. He built a magnificent observatory on an island in the Baltic Sea, equipping it with the most accurate astronomical instruments of his era. And for years he meticulously charted the behaviour of Mars, which stubbornly refused to fit into any existing model. Tycho realised he needed help. He needed a brilliant mathematician to make sense of his mountain of data. He turned his attention to a young German named Johannes Kepler, whose mathematical prowess he knew from their correspondence. Learning of Kepler's personal and professional difficulties, Tycho invited him to Prague. In January of 1600, Kepler arrived. He was a supporter of Copernicus, and he became Tycho's assistant. Their primary task was to create a new model of the universe that could reconcile the data with theory. And Mars, the wanderer, was the key. According to Tycho's incredibly precise measurements, the orbits of Mars and the Sun had to intersect, which called into question all previous ideas. The collaboration was famously fraught with tension. Tycho was secretive and jealously guarded his data, while Kepler was desperate to get his hands on it. Then, in 1601, Tycho Brahe died suddenly. Kepler inherited his mentor's treasure trove of observations. Analysing the data, Kepler embarked on what he called his war with Mars. For years, he struggled to fit the planet's orbit into a perfect circle, trying dozens of variations, but the data would not yield. The discrepancy was tiny, a matter of just 8 minutes of arc, but Kepler, in a testament to his scientific integrity, refused to ignore it. He trusted Tycho's data. He wrote, "Out of these 8 minutes, we will weave our way to a new theory that will completely reform astronomy." And he did. He made a revolutionary discovery. The orbits of the planets were not circles, as everyone from the ancient Greeks to Copernicus had assumed. They were ellipses. This single realization shattered a 2,000-year-old belief in the perfection of the heavens. It was a messy, imperfect solution for a messy, imperfect universe. And it worked. Kepler had long held to the idea of circular orbits himself, but his calculations relentlessly pointed in another direction. The planets, including Mars, moved on elliptical paths with the Sun at one of the two foci. He discovered that the shape of the orbit depended on the distance from the Sun. The closer the planet, the more circular its orbit. He also found that planets move faster when they are closer to the Sun, and slower when they are farther away. These discoveries, his first two laws of planetary motion, finally explained why Mars periodically appears to reverse its direction in the sky. The retrograde motion was an illusion, created as the faster-moving Earth on its inner orbit overtakes the slower-moving Mars on its outer orbit. In 1609, Kepler published his findings in Astronomia Nova, the New Astronomy. As the great science writer Isaac Asimov wrote, Kepler's model explained the motions of the planets so beautifully and simply that there was no longer any doubt that all the planets really did revolve around the Sun. It was then that the system began to be called the Solar System. Galileo, meanwhile, was making his own revolutionary discoveries. His telescopic observations allowed him to perceive changes in the apparent size of Mars as its distance from Earth varied, which reinforced his confidence in Copernicus's theory. Although he couldn't make out surface details, his work confirmed that the planets were worlds in their own right, orbiting the Sun. For his open support of the heliocentric system, he was accused of heresy. In 1632, he published his dialogue concerning the two chief world systems, which brought the wrath of the Church down upon him. He was forced to publicly recant his beliefs to avoid a terrible fate. He spent the rest of his life under house arrest, but his work, his courage, inspired generations of scientists to keep questioning, to keep exploring the heavens. One of those was the Italian astronomer Francesco Fontana. Using high-quality telescopes of his own making, between 1636 and 1639, he noticed dark spots on the disk of Mars. By tracking their movement, he suggested that the planet was rotating on its axis. His drawings were the first attempts to map another world. Another prominent astronomer, Giovanni Cassini, meticulously charted the planet's motion and created more detailed drawings of its surface features. Then came the great Dutch scientist Christian Huygens. He systematically studied a dark triangular feature on Mars that we now know as Syrtis Major Planum. By carefully tracking how its position changed over time, Huygens was able to determine the rotation period of Mars, revealing that a Martian day, a sol, is remarkably similar in length to an Earth day, about 24.5 hours. A little detail perhaps, but one that made Mars feel a little less alien, a little more familiar. William Herschel, the English astronomer who discovered Uranus, went even further. He noted the planet's changing seasons and the shrinking and growing of its polar ice caps. For the first time, he measured its diameter, estimating it to be about 55% of Earth's. Herschel also suggested that Mars had an atmosphere, as he perceived changes in dark patches on its surface, which he interpreted as clouds. Then, in August of 1877, during a particularly close approach of Mars to Earth, a so-called Great Opposition, the American astronomer Asaph Hall made a thrilling discovery. He found two tiny moons orbiting the red planet. He named them Phobos and Deimos, Fear and Panic, the mythological companions of the war god Mars. What's remarkable is that their existence had been speculated upon more than a century earlier. Jonathan Swift in Gulliver's Travels and Voltaire in his story Micromegas had both written about Martians having two moons. A lucky guess, or a brilliant piece of logical deduction based on the idea that planets further from the Sun might have more moons? We'll never know. But these moons are strange little worlds. Phobos orbits so fast that it rises in the west and sets in the east, sometimes twice in one Martian day. Deimos, further out, hangs in the sky for more than 2 sols at a time. The same year, 1877, another discovery was announced that would ignite the public imagination like nothing before. The Italian astronomer Giovanni Schiaparelli, peering through his telescope at the Martian surface, perceived a network of fine, straight lines. He called them canali. Now this is where a simple act of translation changed history. In Italian, canali can mean natural channels or straits, but when it was translated into English, it became canals, implying artificial structures, engineered by intelligent beings. Instantly, a myth was born. People began to imagine Martian engineers building vast irrigation systems to carry water from the polar caps to their dying desert cities. Astronomers tried to explain that it was just a hypothesis, a description of faint features at the very limit of perception, but the idea was too compelling. An American astronomer named Percival Lowell became the greatest champion of this idea. He didn't just believe in Martian canals, he saw an entire civilization. He was so convinced that he used his personal fortune to build a state-of-the-art observatory in Flagstaff, Arizona, specifically to study Mars. He was certain that a highly developed ancient Martian civilization was fighting a desperate battle against drought by constructing a planet-wide network of irrigation canals. Lowell became a key figure in popularizing Mars. His lectures, his articles for magazines, and his 3 books filled with intricate maps of the canals captured the public's imagination. Newspapers ran sensational headlines. In 1907, the Wall Street Journal published a story proclaiming, "Astronomical observations proved the existence of conscious, intelligent human life on the planet Mars." A few years later, the New York Times ran with, "Martians build 2 huge canals in 2 years." These ideas inspired writers like Edgar Rice Burroughs and H.G. Wells, whose stories of Martian adventures and invasions shaped our cultural perception of the Red Planet for a century. In scientific circles, however, Lowell's hypotheses were met with deep skepticism. As astronomical instruments improved, other observers, using more powerful telescopes, were simply unable to perceive the canals that Lowell had so meticulously mapped. More and more experts began to suspect that the lines were an optical illusion, a case of the human brain connecting disparate, faint markings into a coherent pattern, amplified by the power of Lowell's fervent imagination. By the mid-20th century, the idea of Martian canals was largely dismissed by the scientific community, and then, in 1965, the Mariner 4 probe flew past Mars. It sent back the first close-up images of another planet's surface, and what did they reveal? No canals, no cities, just a stark, cratered and seemingly lifeless desert. It was a profound blow to the dream of Martian engineers. Mariner 9, in 1971, put the final nail in the coffin, mapping the entire planet in detail. The canals were simply not there. But what's fascinating is that in 1976, the Viking landers found something arguably even more exciting on Mars: the unmistakable traces of ancient riverbeds. It turns out that billions of years ago, water really did flow across the Martian surface, carving channels and forming a vast, branching hydraulic system. And just recently, in 2022, the Perseverance rover took sediment samples from Jezero Crater, the site of a long-vanished ancient lake and river delta. Those samples, when they are eventually returned to Earth, may contain the chemical traces of past life. If they do, we will be closer to solving the Martian mystery than ever before. We will know that we are not alone in the universe, or at least that we were not always alone. So the dream of a grand Martian civilization faded, replaced by a more subtle, but perhaps even more profound reality, the ghost of a habitable world. But the reality of Mars today is harsh. It's a world almost perfectly designed for dying. The atmosphere is so thin that your tears would boil before you had a chance to suffocate. Cosmic radiation bombards the surface relentlessly. The temperatures swing from something akin to a balmy Antarctic day to a cold so deep it defies our everyday experience. The surface is a stark, rocky desert, covered in a fine, powdery dust like flour, studded with sharp rocks and boulders. And yet, there's a severe beauty to it. Carl Sagan saw it. He described it as a landscape full of a unique harmony, boulders scattered by the impact of a distant crater, vast fields of sand dunes, and the subtle traces left by winds carrying the finest particles of dust. The famous red colour, of course, comes from the high iron oxide content of the soil, rust essentially. It explains why the planet has always been the red one. But Mars is not uniform. There's a stark difference between its two hemispheres, a feature known as the Martian dichotomy. The southern two-thirds of the planet are ancient highlands, heavily pockmarked with enormous impact craters, scars from the chaotic early days of the solar system. One of the largest is the Hellas Planitia, a basin about 4 miles deep and over 1,200 miles in diameter. The northern third of Mars, by contrast, is younger, smoother and lower in elevation, covered by vast plains, volcanoes and other geological formations. The volcanoes are now dormant, but data suggests their activity ceased at different times, from billions to perhaps just millions of years ago. In geological time, that's just yesterday. As astronomer William Hartmann believes, some lava flows may have formed less than 10 million years ago. It's possible that Mars is not entirely geologically dead. One of the most astonishing features of the Northern Hemisphere is the Tharsis Bulge, a vast volcanic plateau rising 6 miles above the surrounding plains. It's home to the largest volcano in the entire solar system, Olympus Mons. It's a shield volcano, 16 miles high and 370 miles across. You could fit the entire British Isles on its base. Despite its colossal size, its slopes are so gentle that if you were standing on its flanks, you wouldn't even perceive you were on a mountain. It was formed by countless flows of low-viscosity lava over immense periods of time. Another giant is Alba Patera, the widest volcano on Mars, over 900 miles across, though not as tall as Olympus Mons. And then there's the Valles Marineris, the Mariner Valley. It's not a canyon carved by a river like our Grand Canyon. It's a vast system of tectonic cracks in the planet's crust, formed billions of years ago as the Tharsis Bulge pushed upwards, stretching and ripping the crust apart. The system is 3,000 miles long, 5 miles deep, and in some places over 400 miles wide. It would stretch from the west coast to the east coast of the United States. Our Grand Canyon would be a mere tributary. Mars is also a world of dunes, vast seas of them, particularly in the northern hemisphere, covering an area of 250,000 square miles. Many are actively moving, shaped by the thin Martian winds. Due to the weak gravity, some ripples and dunes can reach heights of up to 20 feet, far larger than their terrestrial counterparts. But what about the inside of Mars? That's still a challenge to study because we don't have the kind of detailed seismological data we have for Earth from earthquakes. But we can infer its structure. Unlike Earth, Mars does not seem to have active plate tectonics. As Professor David Stevenson of Caltech noted, this means materials on Mars are not recycled. Rocks that are 4 billion years old are often found on the surface. There's been virtually no crustal recycling for billions of years, and that's one of the reasons volcanoes like Olympus Mons could grow to such an enormous size. On Earth, the moving tectonic plates would have carried a volcano off its hotspot long before it could reach such proportions. But on Mars, the crust stayed put, and the volcano just kept growing and growing for aeons. Scientists believe that, like Earth, Mars has a 3-layer structure: a core, a mantle, and a crust. The crust is significantly thicker than Earth's, especially under the Tharsis Bulge. The mantle is thought to be a dense, semi-solid layer similar to Earth's, and we're fairly certain it has a core made of dense material, most likely iron and sulfur. But here's the crucial difference. Mars lacks a strong global magnetic field. This strongly suggests that its core is no longer active and churning like Earth's liquid outer core, and the loss of that magnetic field, that protective shield, may be the single most important reason why Mars is the world it is today. But how does the loss of a planet's internal heat engine lead to the death of its surface? Well, the atmosphere of Mars is the ghost of what it once was. Almost 95% of it is carbon dioxide, whereas on Earth, that gas makes up less than 1%. The rest is nitrogen, argon, and just the faintest traces of oxygen and water vapour. But the key thing is its density. The The atmospheric pressure at the surface of Mars is only about 1% of Earth's. It's comparable to the atmosphere 19 miles above our planet. This rarefied air is unable to retain heat or to shield the surface from the sun's harsh ultraviolet radiation. If you were to release a balloon inflated on Earth onto the surface of Mars, it would instantly explode due to the lack of external pressure. The climate is, as a result, wildly unpredictable. One week, the sky might be a hazy pink, saturated with dust, with a relatively warm temperature of about -40 degrees Fahrenheit. A few days later, the dust might settle, the atmosphere could cool by another 40 degrees, and delicate clouds of ice crystals might appear in the dark sky. These abrupt shifts are driven by the thin atmosphere and Mars's elliptical orbit, which causes significant seasonal variations. When Mars is at its closest point to the Sun, its southern hemisphere receives 40% more sunlight than when it's at its farthest point, but the most dramatic atmospheric phenomenon on Mars is its dust storms. They can be astonishing in their scale and duration. In 2001, a global dust storm enveloped the entire planet for 3 months, completely obscuring the surface from our orbital probes. These storms start small but can quickly grow, filling the atmosphere with a dense reddish haze. The dust particles heated by the sun warm the atmosphere around them, which only intensifies the storm in a runaway feedback loop. And although the winds aren't strong enough to knock over a spaceship, as you might have perceived in films, the air is too thin for that. The dust they carry is a serious hazard for robotic and one day human explorers. Clouds are another interesting feature. Even with minimal water vapour, there's enough to form ice crystals at high altitudes. These crystals, combined with dust, create clouds of various colours: white, pink, brown. And in the lowlands, fogs can form, blanketing craters and valleys in the cold Martian mornings, only to dissipate as the weak sun warms the ground by midday. The polar caps themselves are made of both frozen carbon dioxide, dry ice, and water ice. They shrink and grow with the seasons as the dry ice sublimates into the atmosphere in summer and refreezes in winter. Liquid water is impossible on the surface of Mars today due to the low pressure and extreme cold. It would either instantly boil away or freeze solid. But the evidence of its past carved into the very landscape is undeniable. So where did the water go? Some of it is locked away as ice in the polar caps and as permafrost beneath the surface, but much of it, along with the planet's once thicker atmosphere, was lost to space. And this brings us back to the magnetic field. Earth's magnetic field acts as a shield, deflecting the solar wind, a constant stream of charged particles from the sun. Without this shield, the solar wind would strip away our atmosphere over geological time. Mars, being smaller than Earth, cooled more quickly. Its internal dynamo, the churning liquid iron core that generated its magnetic field, seized up billions of years ago. Left defenseless, the solar wind scoured the Martian atmosphere, carrying away its gases, molecule by molecule over aeons. The water molecules were broken apart by solar radiation, and the light hydrogen atoms escaped into space, while the oxygen reacted with the iron-rich rocks to give Mars its characteristic rusty red colour. Mars literally rusted to death. And this raises an intriguing possibility. If there was once abundant water on Mars, could life have existed there? Even today, hidden reservoirs of water, perhaps in the form of briny aquifers deep underground, could potentially harbour microbial life. Finding it would be one of the most profound discoveries in human history. It would tell us that life is not a unique miracle of Earth, but a common cosmic phenomenon. Robert Zubrin, a passionate advocate for Mars exploration, described it as a world that takes your breath away. And he's right. Mountains 3 times the height of Everest, canyons that dwarf our own, vast ice fields and the ghostly outlines of dried-up riverbeds. This planet doesn't just offer us natural wonders, it offers us answers to some of the deepest philosophical questions we can ask. But those mysteries will remain just out of reach until we go there ourselves. Zubrin argues, and I think he has a point, that it is humanity, not our robotic proxies, that possesses the unique abilities needed to truly explore Mars. A human geologist on Mars could do in a week what a rover might take years to accomplish. Humans can think on their feet, they can adapt, they can draw conclusions from subtle clues, They can experience that flash of intuition that leads to discovery. A rover can analyze a rock, but it can't have a hunch. Mars requires a human presence to reveal its deepest secrets, especially the secret of whether it ever hosted life, or perhaps if it still does. The idea of sending humans to Mars is not new. One of its earliest and most brilliant proponents was Wernher von Braun. After the Second World War, he envisioned a grand expedition, a whole fleet of spacecraft. He believed that, like Columbus, a mission to Mars required a broad, robust approach. In the 1950s, he developed a detailed blueprint for an expedition involving 10 spacecraft and a crew of 70. His plans were far too ambitious for their time, but they inspired generations of scientists and engineers. The reality of a manned mission to Mars depends not just on technology, but on the courage of those who would undertake such a journey. The years away from home, the immense risks, the need for complete self-reliance, it would be the most challenging expedition in human history. But the interest remains enormous. In the early 2000s, President George W. Bush announced a vision for space exploration that included returning to the Moon as a stepping stone to Mars. The first human expedition will be a true test of our capabilities. The astronauts will have to survive a 6-month journey through deep space, exposed to radiation and the risk of micrometeorites. Arriving on the surface will actually reduce some of those threats. The planet itself will provide some shielding, but Mars will present its own, entirely new set of challenges. One of the biggest is the extremely low atmospheric pressure. Without a pressurized spacesuit, a human's body fluids would literally boil and evaporate in seconds. The Martian air is unbreathable, a toxic cocktail of carbon dioxide with only minimal traces of oxygen. The climate is another major hurdle. The temperature can swing dramatically. A few feet above the ground, it can be 20 or 30 degrees colder than at your feet. Spacesuits will have to keep astronauts warm in this brutally cold environment. And then there's the dust. That fine, pervasive dust. We're still not sure how toxic it is, but it will get into everything, limiting visibility and potentially affecting breathing equipment. And of course, the dust storms. They can last for weeks, with winds reaching speeds of up to 100 miles per hour. Developing the perfect spacesuit is a complex challenge. It must be lightweight and flexible, yet incredibly durable and reliable. The first astronauts on Mars will be explorers in the truest sense of the word. They will be geologists searching for signs of past water, studying rocks, drilling into the surface and analysing samples. All of this requires suits that provide freedom of movement and long-lasting protection. We don't have such a suit yet, but the technology is within our reach. And while our engineers work on these immense challenges, another even bolder idea is brewing. If we can learn to survive on Mars, why not dream of a future where it becomes a new home for humanity? This is the idea of terraforming, transforming Mars into an Earth-like planet. The term was first coined by the science fiction writer Jack Williamson in 1942, but the idea is older. Olaf Stapledon, in his epic novel Last and First Men, proposed changing Venus to meet human needs. But it was Carl Sagan who first brought the idea into the realm of serious scientific discussion. In 1961, he proposed seeding the atmosphere of Venus with algae to convert carbon dioxide and reduce its runaway greenhouse effect. For Mars, he suggested that warming the polar caps could release enough carbon dioxide to thicken the atmosphere. Serious models only began to appear in the 1970s, after the Mariner and Viking missions revealed that Mars did indeed have vast reserves of frozen carbon dioxide and water, and had once possessed a thicker atmosphere. Science fiction set the stage, and science followed when the data became available. But before we can even think about how to terraform Mars, we have to fully understand why it became the frozen desert it is today. As we've touched upon, the prime suspect is the loss of its magnetic field. Without that protective shield, the solar wind stripped away its atmosphere. But there are other theories. Some scientists point to the evidence of colossal supervolcanoes in Mars's past. Eruptions on a scale we can barely imagine could have choked the atmosphere with dust and toxic gases, blotting out the sun for centuries and plunging the planet into a deep freeze from which it never recovered. And not all the water escaped into space. A significant amount is likely trapped underground as ice, or chemically bound within the planet's rocks. The Martian crust is full of minerals that can absorb water like a sponge, so some of the planet's lost oceans are literally locked away in stone. The question of whether Mars was ever truly habitable is also complex. Recent data from the Curiosity and Perseverance rovers suggest that while water was present, it may have been highly acidic and salty, not exactly a nourishing primordial soup, but it might have been good enough for hardy microbes, perhaps thriving in protected niches underground. If we find evidence of them, it would revolutionize our understanding of life in the universe. Today, the surface of Mars is a realm of extremes, but it's not a static, frozen world. It's dynamic. The Martian year lasts 687 Earth days, and it has seasons just like Earth. In winter, carbon dioxide in the atmosphere freezes out at the poles, creating dry ice snowfalls. In spring, this ice sublimates, turning directly from a solid into a gas. This process creates some fascinating phenomena, like strange spider-like patterns that form at the South Pole as jets of gas burst through the ice, scattering dark dust across the surface. And Mars quakes. We used to think it was geologically dead, but the InSight lander, which listened for seismic tremors, showed that the planet's interior is still stirring. There may still be pockets of liquid magma deep inside. The strongest Marsquake recorded in 2022 was a magnitude 4.7. That's a significant tremor. It means Mars hasn't completely cooled down yet. But perhaps the most tantalizing mystery is the methane. Both the Curiosity rover and the ExoMars Trace gas orbiter have detected seasonal plumes of methane in the Martian atmosphere. More in summer, less in winter. Where does it come from? It could be from geochemical reactions deep underground. But there's another possibility. On Earth, 90% of the methane in our atmosphere is produced by living organisms. If there are microbes deep beneath the Martian surface, producing methane as a waste product, it would be a discovery of monumental importance. So why did we suddenly start to believe that we could fix an entire planet? Perhaps it was the Apollo 8 effect. In 1968, for the first time, humans saw our own planet from lunar orbit, a fragile, beautiful blue and white sphere hanging in the black void, and that image changed everything. It gave us a profound sense of our own vulnerability. If we were to accidentally destroy our home, where else could we go? And the answer, inevitably, was Mars. It became our lifeboat, our plan B. Terraforming went from being a science fiction dream to a potential engineering challenge. And as we learned more about Mars's past, that it was once a warm, wet world, the question became, could we turn back the clock? The first idea that comes to mind is to create a new greenhouse effect. Given that the main problem is the cold and the thin atmosphere, the challenge is to warm the planet up. One of the most dramatic and controversial proposals came from Elon Musk in 2015. He suggested detonating thermonuclear weapons over the polar ice caps. The idea is to create pulsating suns that would vaporize the frozen carbon dioxide, releasing it into the atmosphere. The sudden release of this greenhouse gas would, in theory, begin to trap more of the sun's heat, raising the planet's temperature and starting a runaway warming process. But would it work? When a nuclear device detonates, the temperature at its epicenter reaches tens of millions of degrees, comparable to the core of the sun. This intense energy is released as X-rays and gamma rays, creating a blindingly bright fireball that expands rapidly. The resulting shockwave would vaporize the ice and throw vast quantities of gas and dust into the atmosphere. On Mars, where the soil and polar caps contain significant amounts of frozen water and carbon dioxide, an underground explosion would have a similar effect, creating a massive crater and liberating these trapped volatiles. However, there's a catch, and it's a big one. Our best estimates, based on data from our orbital probes, suggest there simply isn't enough easily accessible carbon dioxide on Mars to do the job. Even if we could vaporize all the carbon dioxide in the polar caps and bound in the surface dust, it would only increase the atmospheric pressure to perhaps 20 millibars at best. The current pressure is about 6 millibars. For comparison, the atmospheric pressure on Earth is about 1,013 millibars, so we would still have an atmosphere only about 2% as thick as our own. it's not enough to create a significant greenhouse effect or to allow liquid water to be stable on the surface. It's a step, but it's a very small one. A nuclear explosion would be a dramatic but ultimately inefficient way to start the process. So what about a more gentle approach? Instead of bombs, what about giant mirrors? Huge lightweight mirrors could be placed in orbit around Mars, focusing sunlight onto the polar caps. Unlike a nuclear explosion, this method is controllable and precise. These solar concentrators would act like giant magnifying glasses, heating the ice sheets and causing the frozen carbon dioxide to sublimate directly into the atmosphere. The advantage is that this could be a continuous process. But it faces its own challenges. The Martian atmosphere, though thin, is full of dust. This dust would settle on the mirrors, reducing their efficiency. They would need some form of self-cleaning mechanism. And again, we come back to the fundamental problem. There just isn't enough carbon dioxide available to make a big difference. We would raise the temperature by a few degrees, but not enough to trigger a self-sustaining climate shift. This is where the idea of In-Situ Resource Utilization, or ISRU, becomes crucial. Instead of just releasing what's already there, what if we could manufacture what we need from the raw materials on Mars? The Martian soil, the regolith, is a mixture of basaltic dust, perchlorates, and, in many places, subsurface ice. We could develop robotic mining systems that heat the ground, causing the ice to sublimate into water vapor, which can then be collected and condensed. This water is the key. Once we have water, we can use electrolysis to split it into hydrogen and oxygen. The Perseverance rover has already demonstrated this principle on a small scale with its MOXIE instrument. MOXIE, which stands for Mars Oxygen In-Situ Resource Utilization Experiment, successfully produced small amounts of oxygen from the Martian atmosphere's carbon dioxide. MOXIE is a marvel of engineering. It inhales the thin Martian air, compresses it, and then heats it to about 800 degrees Celsius. At this high temperature, it uses solid oxide electrolysis to split the carbon dioxide molecules into oxygen and carbon monoxide. The oxygen is stored, and the carbon monoxide is vented back into the atmosphere. In its first test, it produced about 5 grams of oxygen in an hour, enough to sustain an astronaut for about 10 minutes. Over its mission, it has proven to be reliable, producing up to 12 grams per hour. To support a human crew, we'd need a system about 100 times larger, capable of producing 2 to 3 kilograms of oxygen per hour. And for rocket fuel to return to Earth, we'd need about 25 tons of it. It's a huge engineering challenge, but MOXIE has shown that the principle is sound. But simply producing oxygen isn't enough to change the atmosphere. We need to enhance the greenhouse effect. One way to do this would be to manufacture powerful, artificial greenhouse gases on Mars. Compounds like sulfur, hexafluoride, or perfluorocarbons are thousands of times more effective at trapping heat than carbon dioxide. The raw materials to make them, including fluorine, are present in the Martian regolith. We could build factories that would synthesize these compounds and release them into the atmosphere. Even in small concentrations, they could significantly raise the planet's temperature. This could create a positive feedback loop. The initial warming would release more carbon dioxide from the poles, which would cause more warming, and so on. Another idea is to import the necessary materials. We could redirect ammonia-rich asteroids or comets from the outer solar system to crash into Mars. The impacts would release vast amounts of energy, warming the planet, and the ammonia itself is a potent greenhouse gas. It would also provide a source of nitrogen, which is a crucial buffer gas in Earth's atmosphere, making up 78% of the air we breathe. Or we could import hydrogen, which could be reacted with the iron oxide in the Martian soil to produce water, and with the atmospheric carbon dioxide to produce methane, another powerful greenhouse gas, through a process called the Sabatier reaction. This Sabatier reaction is particularly elegant because it creates a closed-loop system. The carbon dioxide from the atmosphere is reacted with hydrogen, from water electrolysis, to produce methane and water. The methane can be used as rocket fuel. The water can be fed back into the electrolysis unit to produce more hydrogen and oxygen. It's a way of bootstrapping a fuel production industry using local resources. We could also try to reduce Mars's albedo, its reflectivity. The Martian surface is quite bright, and it reflects a lot of sunlight back into space. If we could make the surface darker, it would absorb more heat. We could do this by spreading dark dust, perhaps mined from Mars's moons, Phobos and Deimos, which are among the darkest objects in the solar system. Or, in a more advanced stage, we could introduce hardy, dark-coloured microorganisms like lichens or algae that could survive in the harsh Martian environment and gradually darken the surface. So, you can perceive how all these different ideas could be combined into a grand, multi-stage strategy. Orbital mirrors and artificial greenhouse gases provide the initial warming. This releases some of the natural carbon dioxide, thickening the atmosphere. This increased pressure makes it easier for robotic factories to operate, producing more greenhouse gases, as well as oxygen and methane fuel using local water and atmospheric carbon dioxide. Controlled asteroid impacts add more heat and volatile materials, and gradually, over centuries or even millennia, the climate of Mars could be shifted towards a state where liquid water could once again flow on its surface. It's an incredible vision, but let's be clear, this is all speculative. Modern technology is nowhere near capable of achieving it. Our most recent and thorough studies, based on data from our Mars orbiters, have concluded that there simply isn't enough carbon dioxide available on Mars to be released to create a significant greenhouse effect. As Bruce Jakosky of the University of Colorado, a leading expert on the Martian atmosphere, has stated, even if we could release all the carbon dioxide locked in the polar caps and minerals, it would only get us to about 1.2% of Earth's atmospheric pressure. The energy required to extract carbon dioxide from minerals would be immense, requiring temperatures over 300 degrees Celsius on a planetary scale. And even if we could thicken the atmosphere, the solar wind is still there, constantly stripping it away. Without a new artificial magnetic field to protect the planet, any atmosphere we create would eventually be lost. The logistical challenges are also staggering. Delivering, deploying, and maintaining the vast industrial infrastructure required for terraforming is far beyond our current capabilities. So while we dream of a green Mars, the data tells us a different story. For now, Mars remains a profoundly inhospitable world. Any large-scale terraforming effort must be postponed to a distant future, when we might have breakthrough technologies that we can't even imagine today. So, if terraforming is a distant dream, what about the more immediate goal of just sending humans there? That is a challenge for our generation. And it's not just about the rockets and the hardware. It's about preparing a crew physically and psychologically for the most arduous journey ever undertaken. The training alone will take years, perhaps up to a decade. It will involve mastering piloting, robotics, geology, and medicine, and the psychological preparation will be just as crucial. Astronauts will have to cope with years of isolation, confined in a small space, millions of miles from home. We use analog environments on Earth to simulate these conditions, research stations in Antarctica or undersea habitats. Once on Mars, the crew will have to be almost entirely self-sufficient. Since it's so expensive to launch mass from Earth, the habitats will likely be inflatable modules, sent ahead and deployed robotically. The ice home concept, for example, envisions an inflatable dome covered with a thick layer of Martian ice, which would provide excellent protection from radiation. NASA is already testing 3D printed habitats in its Sapatier program, where volunteer crews live for a year at a time in a simulated Martian base at the Johnson Space Center. These modules will have to be homes, laboratories, and command centers all in one, and life inside will be a constant challenge. Everything we take for granted on Earth becomes a complex problem. Waste disposal, for instance. On the International Space Station, rubbish is packed into departing cargo ships to burn up in Earth's atmosphere. On Mars, that's not an option. We'll need advanced compactors and recycling systems. The Soviet Bios 3 experiment in the 1970s was a pioneering attempt at a closed-loop life support system. It was a sealed habitat where a small crew lived for up to 6 months, with air and water recycled by algae and higher plants, which also provided up to 80% of their food. The technologies developed for Bios 3 are the ancestors of the systems that will be needed for a Martian base. And then there's the human element. Time itself will be different. A Martian sol is 39 minutes longer than an Earth day. This constant desynchronization will affect circadian rhythms. The The crew will have to be trained to perform complex medical procedures on each other, as there will be no possibility of an emergency evacuation. Even simple illnesses could become life-threatening. Hygiene will be a constant battle against the pervasive Martian dust. Showers will be carefully rationed with every drop of water recycled, and the psychological strain of living with the same few people, with no escape, will be immense. The crew will need private time, recreation, and a constant, albeit delayed, connection to their families back on Earth. Every piece of equipment will have to be repairable. The Apollo 13 astronauts famously saved their mission using duct tape, a plastic bag, and a cardboard manual cover. The first Martian explorers will need that same ingenuity, but on a daily basis. They will be the ultimate mechanics and problem solvers, and after a long, grueling day of work, they will need to rest. But even sleep is different. In weightlessness, astronauts can sleep anywhere. On Mars, with its 1/3 gravity, they will need bunks, and they will have to get used to the simple act of lying down again. Free time will be essential. On the ISS, astronauts watch movies, read, play music, and spend hours just gazing out of the cupola window at the Earth passing below. For the Mars crew, the view will be of a vast static orange landscape. Homesickness will be a constant companion. The familiar sounds and smells of Earth, birdsong, rain, the scent of grass, will be absent. They will be utterly, profoundly alone. And this brings us back to the fundamental question: why? Why endure all this hardship, this risk, this expense? The feeling that our own planet is becoming increasingly fragile is a powerful motivator. The litany of challenges we face, climate change, conflict, resource depletion, creates a sense that we cannot afford to keep all our eggs in one basket. Mars represents a chance to start again, to build a new branch of human civilization, one that can learn from our mistakes. It's not about abandoning Earth. It's about ensuring the long-term survival of our species. It is a profound expression of hope. On May 6, 1970, Dr. Ernst Stühlinger, a key figure at NASA and a close colleague of Wernher von Braun, received a letter from a nun named Sister Mary Chikunda, who was working in Zambia. She asked a simple, powerful question. How could he advocate for spending billions of dollars to go to Mars when so many children on Earth were starving? Stühlinger's reply is, I think, one of the most eloquent and moving defenses of space exploration ever written, and I'd like to share it with you. He wrote, Dear Sister Mary Chikunda, your letter was one of many which are reaching me every day, but it has touched me more deeply than all the others because it came so much from the depths of a searching mind and a compassionate heart. I will try to answer your question as best as I possibly can. First, however, I would like to express my great admiration for you and for all your many brave sisters because you are dedicating your lives to the noblest cause of man, help for his fellow men who are in need. You asked in your letter how I could suggest the expenditures of billions of dollars for a voyage to Mars at a time when many children on this earth are starving to death. I know that you do not expect an answer such as, oh, I did not know that there are children dying from hunger, but from now on I will desist from any kind of space research until mankind has solved that problem. In fact, I have known of famine children long before I knew that a voyage to the planet Mars is technically feasible. However, I believe, like many of my friends, that travelling to the Moon, and eventually to Mars and to other planets, is a venture which we should undertake now, and I even believe that this project, in the long run, will contribute more to the solution of these grave problems we are facing here on Earth than many other potential projects of help which are debated and discussed year after year, and which are so extremely slow in yielding tangible results. Before trying to describe in more detail how our space program is contributing to the solution of our earthly problems, I would like to relate briefly a supposedly true story, which may help support the argument. About 400 years ago, there lived a count in a small town in Germany. He was one of the benign counts, and he gave a large part of his income to the poor in his town. This was much appreciated because poverty was abundant during medieval times, and there were epidemics of the plague which ravaged the country frequently. One day, the Count met a strange man. He had a workbench and little laboratory in his house, and he laboured hard during the daytime so that he could afford a few hours every evening to work in his laboratory. He ground small lenses from pieces of glass. He mounted the lenses in tubes, and he used these gadgets to look at very small objects. The Count was particularly fascinated by the tiny creatures that could be observed with the strong magnification and which he had never seen before. He invited the man to move with his laboratory to the castle, to become a member of the Count's household, and to devote henceforth all his time to the development and perfection of his optical gadgets as a special employee of the Count. The townspeople, however, became angry when they realized that the Count was wasting his money, as they thought, on a stunt without purpose. "We are suffering from this plague," they said, "while he is paying that man for a useless hobby." But the Count remained firm. "I give you as much as I can afford," he said, "but I will also support this man and his work because I know that someday something will come out of it." Indeed, something very good came out of this work, and also out of similar work done by others at other places: the microscope. It is well known that the microscope has contributed more than any other invention to the progress of medicine, and that the elimination of the plague and many other contagious diseases from most parts of the world is largely a result of studies which the microscope made possible. The Count, by retaining some of his spending money for research and discovery, contributed far more to the relief of human suffering than he could have contributed by giving all he could possibly spare to his plague-ridden community. The situation which we are facing today is similar in many respects. The President of the United States is spending about $200 billion in his yearly budget. This money goes to health, education, welfare, urban renewal, highways, transportation, foreign aid, defense, conservation, science, agriculture, and many installations inside and outside the country. About 1.6% of this national budget was allocated to space exploration this year. The space program includes Project Apollo and many other smaller projects in space physics, space astronomy, space biology, planetary projects, Earth resources projects, and space engineering. To make this expenditure for the space program possible, the average American taxpayer with $10,000 income per year is paying about $30 tax dollars for space. The rest of his income, $9,970, remains for his subsistence, his recreation, his savings, his other taxes, and all his other expenditures. You will probably ask now, why don't you take $5 or $3 or $1 out of the 30 space dollars which the average American taxpayer is paying and send these dollars to the hungry children? To answer this question, I have to explain briefly how the economy of this country works. The situation is very similar in other countries. The government consists of a number of departments and bureaus. All of them prepare their annual budgets according to their assigned missions, and each of them must defend its budget against extremely severe screening by congressional committees and against heavy pressure for economy. When the funds are finally appropriated by Congress, they can be spent only for the line items specified and approved in the budget. The budget of the National Aeronautics and Space Administration, naturally, can contain only items directly related to aeronautics and space. If this budget were not approved by Congress, the funds proposed for it would not be available for something else. They would simply not be levied from the taxpayer unless one of the other budgets had obtained approval for a specific increase, which would then absorb the funds not spent for space. You realize from this brief discourse that support for hungry children can be obtained only if the appropriate department submits a budget line item for this purpose, and if this line item is then approved by Congress. You may ask now whether I personally would be in favour of such a move by our government. My answer is an emphatic yes. Indeed, I would not mind at all if my annual taxes were increased by a number of dollars for the purpose of feeding hungry children wherever they may live. I know that all of my friends feel the same way. However, we could not bring such a program to life merely by desisting from making plans for voyages to Mars. On the contrary, I even believe that by working for the space program, I can make some contribution to the relief and eventual solution of such grave problems as poverty and hunger on Earth. Basic to the hunger problem are two functions: the production of food and the distribution of food. Food production is efficient in some parts of the world, but drastically deficient in many others. Large areas of land could be utilized far better if efficient methods of watershed control, fertilizer use, weather forecasting, fertility assessment were applied. The best tool for the improvement of all these functions, undoubtedly, is the artificial Earth satellite. Circling the globe at a high altitude, it can screen wide areas of land within a short time. It has been estimated that even a modest system of Earth satellites, equipped with Earth resources sensors, working within a program for worldwide agricultural improvements, will increase the yearly crops by an equivalent of many billions of dollars. The distribution of the food to the needy is a completely different problem. It is one of international cooperation. I do not believe that spaceflight will accomplish this miracle overnight. However, the space program is certainly among the most promising and powerful agents working in this direction. Let me only remind you of the recent near tragedy of Apollo 13. When the time of the crucial re-entry of the astronauts approached, the Soviet Union discontinued all Russian radio transmissions in the frequency bands used by the Apollo project in order to avoid any possible interference, and Russian ships stationed themselves in the Pacific and the Atlantic Oceans in case an emergency rescue would become necessary. If Russian space travelers should ever be in a similar emergency situation, Americans would do the same without any doubt. Higher food production through survey from orbit and better food distribution through improved international relations are only two examples of how profoundly the space program will impact life on Earth. I would like to quote two other examples: stimulation of technological development and generation of scientific knowledge. The requirements for high precision and for extreme reliability, which must be imposed upon the components of a moon-travelling spacecraft, are entirely unprecedented in the history of engineering. All this newly acquired technical knowledge is also available for application to Earthbound technologies. Every year, about 1,000 technical innovations generated in the space program find their ways into our earthly technology, where they lead to better kitchen appliances and farm equipment, better sewing machines and radios, better ships and airplanes, better weather forecasting and storm warning. Presumably you will ask now why we must develop first a life support system for our moon-travelling astronauts before we can build a remote reading sensor system for heart patients. The answer is simple. Significant progress in the solutions of technical problems is frequently made not by a direct approach, but by first setting a goal of high challenge which offers a strong motivation for innovative work, which fires the imagination and spurs men to expend their best efforts, and which acts as a catalyst. Spaceflight, without any doubt, is playing exactly this role. The voyage to Mars will certainly not be a direct source of food for the hungry. However, it will lead to so many new technologies and capabilities that the spin-offs from this project alone will be worth many times the cost of its implementation. Besides the need for new technologies, there is a continuing great need for new basic knowledge in the sciences if we wish to improve the conditions of human life on Earth. Again, the space program, with its wonderful opportunities to engage in truly magnificent research studies of moons and planets, is an almost ideal catalyst. Among all the activities which are directed, controlled and funded by the American government, the space program is certainly the most visible and probably the most debated activity. As a stimulant and catalyst for the development of new technologies and for research in the basic sciences, it is unparalleled by any other activity. In this respect, we may even say that the space program is taking over a function which for 3,000 or 4,000 years has been the sad prerogative of wars. How much human suffering can be avoided if nations, instead of competing with their bomb-dropping fleets of airplanes and rockets, compete with their moon-travelling spaceships? This competition is full of promise for brilliant victories, but it leaves no room for the bitter fate of the vanquished, which breeds nothing but revenge and new wars. Although our space program seems to lead us away from our Earth and out towards the moon, the sun, the planets and the stars, I believe that none of these celestial objects will find as much attention and study by space scientists as our Earth. It will become a better Earth, not only because of all the new technological and scientific knowledge which we will apply to the betterment of life, but also because we are developing a far deeper appreciation of our Earth, of life, and of man. The photograph which I enclose with this letter shows a view of our Earth as seen from Apollo 8 when it orbited the Moon at Christmas 1968. Of all the many wonderful results of the space program so far, this picture may be the most important one. It opened our eyes to the fact that our Earth is a beautiful and most precious island in an unlimited void, and that there is no other place for us to live but the thin surface layer of our planet, bordered by the bleak nothingness of space. Never before did so many people recognize how limited our Earth really is, and how perilous it would be to tamper with its ecological balance. Ever since this picture was first published, voices have become louder and louder, warning of the grave problems that confront man in our times: pollution, hunger, poverty. It is certainly not by accident that we begin to see the tremendous tasks waiting for us at a time when the young space age has provided us with the first good look at our own planet. Very fortunately, though, the space age not only holds out a mirror in which we can see ourselves, it also provides us with the technologies, the challenge, the motivation, and even with the optimism to attack these tasks with confidence. What we learn in our space program, I believe, is fully supporting what Albert Schweitzer had in mind when he said, "I am looking at the future with concern but with good hope.